let me set a couple of things here. Okay, I hope you guys are doing okay. All right, and then we are meeting again today, and we're going to continue the discussion of the well, it's a continuation from oscillations, and the topics that we're going to cover today is waves now. All right, and I hope it's inclusive today in terms of we're going to learn how to deal with waves and how can we describe wave in sort of like using mathematics and what is the properties of waves. That's coming a little bit later on. All right, but we're going to start with mathematics first. Okay, let me just give me 1 second here. I'm just testing again. Yeah, just wondering what happens if I'm at MUIC campus. I'm so thank you for sort of like agree with me that we continue doing online class just for now because I am sort of well, I don't have any confidence setting up things over there. Okay, so I hope things is going okay. I mean, for now, and then hope that next week when I set up there, it's going to be okay. Yeah. The only concern that I have was the connections because my setup right here, there are a couple of devices that need like internet at the same time, and I'm not sure that I am allowed to have multiple login using MUIC servers. So I'm not so sure. All right. Okay. All right. I think that's good. All right, let's get started, guys. I think I'm gonna turn this thing off now. Okay. All right. Okay. So wait 1 second. It's not off. I have to leave the meeting. I'm just using another device to connect through mobile network, and I hope it seems to be okay. Alrighty. Okay, guys. So what we are trying to understand today is the phenomena called waves. All right. And just to get things started, once again, I'm going to use a simulation. All right. And I hope it will sort of give you the overview of what we are trying to do. So I'm going to share another screen here, which looks like this. Where is going here? That's not I intended to do. So see, so I'm confused right now. Okay, so let's share this screen. Nope, not going. Okay, let me move it back here. It's only share this screen right here. Okay, let's do one more try. Okay, here you go. I hope it works now. Oh, I have to. Okay, all right. So, um, the simulation once again, I'm using the physics simulation here. I can sort of go back a little bit so you guys can try this one as well. Okay, I have to move something so you guys know what it's not like a static figure. Okay, very good. All right. Okay, here we go. Okay, I'll rerun the whole thing one more time. So I'm going to reduce the damping. All right. So just talking about no lose and friction or anything. And I'm going to let the wave just sort of travel out. All right. We don't talk about bouncing wave or anything at this point. All right. We'll discuss that later. Okay. And what we are trying to say is the waves is just a propagation of the disturbance. So that means if you look on the left, all right, when you have the end of the string attached to a device, this is like a vice or something. All right. If I move up and down, I am generating a disturbance. Right? And because the molecule or the elements of the string are attached to each other, and that's level, with the red dot and the green dot that you can see in there. Okay, so those are connecting. You can think of it like a molecules or elements of the string or whatever. So when the movement happens on the left, and each dot or each ball can feel the disturbance of their neighbor, then of course the interaction between atoms or between elements in the string will sort of render the movement of the neighboring atoms as well. And that generates sort of like a chain reaction. You can think of it that way. So the ball A move up, ball B will start moving up, ball C will start to move a little bit later, ball D, I don't know why I use A, B, C, D, I use 1, 2, 3, 4, 5. That is something like that. So, but you see what I'm saying, I'm trying to get to is there is a source of disturbance. All right. And because of the interaction between neighboring atoms, then you can actually transfer this disturbance. All right. And this disturbance that get transferred along the line generate something we call wave. Okay. And the wave that we are going to do is it could be just like a single pulse. So single pulse means there's only single movement, just like you just move your hand once and then that you generate a pulse of wave. All right. So you call that a wave pulse. Or on the other hand, you can do a continuous oscillation. Right? I can do it in a slow motion over here. So you already learned about the oscillation last time, that you can describe something that moves back and forth periodically using sine and cosine function. Okay. So over here, you can see that if you look on the left, okay, look on the leftmost green ball actually move up and down. And if you track that movement, and if that movement is just a simple harmonic, the wave that coming out of it, that is going to be a sinusoidal wave as well. Okay, so what we are going to focus on today is the sinusoidal wave, because we already learned from last lecture, that we use the sine and cosine to describe an oscillating stuff. Right? When things move in the periodic fashion with a single frequency, then you can use sine and cosine. And this is the connection from the oscillations to the waves. The waves that get generated by the source that moving with a simple harmonic motion, you will get the sine and cosine wave as well. Done. That's the whole picture, I hope. Okay. After some hiccup. All right. So I hope you see the whole pictures of what we are trying to do today. And at the end, you will see that you only need a single line of equation to describe everything about wave. And that's it. So that will be the goal of the first half of today's lecture. All right. If you understand that one, that's it. We're done with the waves description. Okay, let's get started here, guys. Okay, so I hope you see the animation now. And oh my God. All right. But the best way to get to this one is you can search the lower right corner. You can see that there is a PHET. You can just do the search on that one. And then you can add like wave on a string in there. It will get right into this simulation. Okay, sounds good. All right, cool. Let's get back to what we have before. How do I stop sharing? Here we go. All right, stop share there. All right, so let's share the handouts one more time. Here we go. Okay. All right, so what we are trying to learn today is this. All right, so in conclusion from the simulation that you have already seen, so you need pretty much three things to generate a wave. Okay, first, of course, you need a source of the disturbance. And of course, you need a medium at this point. And you need some mechanism that adjacent portion of the medium can influence each other. So that means you need some interaction between neighboring atoms or neighboring elements. Okay, so that's it. If you have these three elements, then whenever you have the source of disturbance, that disturbance will get distributed in the form of a wave. Okay, cool. All right, that's the whole thing. Now, in general, when people start talking about waves, they can classify the waves into two types based on how the elements of the medium moves. Okay, so if you look at the first one right here, this one you have is like a spring, a very long one. But then instead of pushing back and forth along the axis of the spring, you can move your hand up and down, and then you can treat the spring just like a string. Like you treat a spring like a string. So in this case, your hand is actually moved up and down. Okay. And of course, the wave traveling to the right in this case. So what you can see over here is if you look at the elements of the spring, it's move up and down, up and down. Okay, wherever you look at this one, it's only move up and down, no matter where you are on the string, which is right now is a spring at this point. But the wave is traveling to the right. And that is the key, guys. This is the difficulty of this subject right here. You have two velocity in one topic right here. Two velocity. You can look, I can say this is the V, the velocity of the wave. But then there is the velocity of each element of the string itself. I can call this, in this case, you can call it transverse if you want. When you say transverse, means the movement of the element is perpendicular to the direction of the movement of the wave. Okay. I can do another way because this is a spring. Instead of move my hand up and down, I can move my hand in and out. You're going to generate a wave anyway. Okay. However, of course, if you're focusing on the element of the wave at one point, it's only going to move left and right. Okay. And you still have the velocity of the wave anyway. The velocity of the wave just travel. You cannot stop it. Okay. And if you look at one particular point on the string, it's only going to oscillate back and forth. In this case, you can call this like a longitudinal velocity. So as you can see, whenever you look at the waves, you always have two velocities to think about. One is the velocity of the wave itself. The wave just go. Okay. And the second is the velocity of the elements of the medium. So it seems like the scenario that I would like to compare this thing with is you imagine yourself like in the sea or something like that. Okay. And then of course, when you're in the sea, you sort of like floating around. There will be like a wave coming through you. But the only thing that's get through you is just the wave. It's just passing you and then just move on. But you only sort of like surf the wave, right? Pretty much you just move up and down, up and down. But you're not going tag along with the wave as long as you're not trying to do windsurfing or anything, right? You just pretty much like, you know, floating in the sea. And then the wave just go through and you only go up and down. You're not going anywhere. You're not sort of move along with the wave. And this is the scenario that you can think of it this way. Okay? You have the velocity of wave that going through you, and you have your own velocity of moving up and down. Okay, so that's what it is. So that is two velocity in one. And that's what we're trying to do. But for the longitudinal, when the elements moving back and forth in the same direction as the velocity of the wave itself, you can still use the same mathematics anyway. So the motion over here and the motion over here, no matter what kind of waves it is a transverse or is a longitudinal, is the same mathematics. And I can just tell you right away, it's going to be sine and cosine. There's nothing else. Okay, it's just you use the same mathematics, but the actual physical movement is just different direction. That's all. Okay, sounds cool. All right, so that's what we are trying to get to. Actually, I have some sort of like some sort of like a spring over here as well. All right, which you can see. I can move my spring up and down. If you can, I mean, I don't know, the refresh rate is good enough, but this is a transverse wave. Okay, so this is a spring. I can move my hand. It's so fast, up and down like this, or I can do in and out, which is not very nice. I can do vertical one, which is so hard to see. So forget about this one. All right, that's why simulation works a little bit better. Okay, all right, that's kind of bad demonstration somehow. All right, but I hope you see what I'm trying to get to. All right, so there are two kinds of waves based on the directions of the motion of the elements of the medium. Transverse, if it's perpendicular to the velocity of waves, and longitudinal, if it's oscillating in the same direction or parallel to the velocity of the waves. But no matter what type, we're using the same mathematics. Okay, so to make things a little bit easier to imagine, we are pretty much going to focus on the transverse case first, because that's sort of like we can say, hey, one is horizontal, the other one is vertical, so they are definitely different type of velocity. Okay, sounds reasonable. Okay, so we're gonna stick with this one first, but in your head, say mathematics. Okay, so let me start from this one, guys. Okay, so suppose we have a wave. It can be a pulse wave, it can be a continuous wave, doesn't matter. Okay, and somehow, because we would like to describe this wave using mathematics, so that means I probably can write down a function that represents this wave right here. Let's call f of x. So this means this is a curve. Okay, but then because this wave has to travel, correct? How can you describe this wave at later time? What do you think? If this is at time 0, the wave look like this. But as I said, the wave is traveling to the right with some velocity or some speed right here. So let me put the speed of waves to be v at this point. What do you think what will happen at times t, later time? The answer is this. I don't know, you sort of see how things goes here, but if not, that's okay. This is what I'm trying to do. Okay, so it's gonna be like the same thing as what you have tried before, but I'm going to start really simply by this. Look at this one. If I have a straight line, okay, 45 degree, very nice, y equal to x. That's simple, correct? If I move this line to the right, look at the green. And let's say I sort of translate this one by the distance a. What is the equation of the green line? What do you think? So everyone can see, this is just exactly the same line, except now you have the y-intercept at negative a. You guys with me? So that means this equation is going to look like x minus a because the slope is still equal to 1, but the y-intercept is negative a. But on the other hand, I can move this line to the left. If I move it by the distance b, so this means the x-intercept will be at negative b. What is the orange line equation? You say, well, Ajahn, that's no big deal because if you move to the left by b, the y-intercept will be at positive b. And this equation will look like y equal to x plus b, yes? So everyone okay with this? Now I'm going to try again with this. Now I'm starting with a parabolic curve, y equal to x squared. Now, what do you think it will happen if I, once again, do the same trick? I'm moving this parabolic curve to the right by the distance a. What will be the green equation? So for those of you that sort of like remember how things goes with the shifting of a curve, yeah, back in mathematics, you see, Bhaijan, this is not bad. The green one is going to look exactly just like y equal to x squared because it's still parabolic curve anyway, except you have to subtract x by that translations distance. Perfect, very good, almost, but x and minus a has to stay together. Okay, guys, with me? Because if you do y equal to x squared minus a, if the a is outside of the x, actually this one is going to be the translation downward. So that will go like this. This is y equal to x squared minus a because you drop down the x squared by a because you subtract out to the a. Okay, sounds good? So that means the x minus a has to stick together. So what I'm saying is the form of the function must stay the same. It must be square function. But then you just turn x into x minus a. Okay, sounds good? One more time. If I translate this parabolic curve to the left instead, by the distance b, what you think is going to be for the orange curve? You say, okay, no problem, Jan. Translation to the left is going to look like x now plus b. And then the whole thing has to keep the form of the square function, x plus b squared. All right, cool. That's good. That's good. All right, so now conclusion is, if the translation is to the right, what you need to do is you turn x into x minus a. Is this the right translation? Okay. And if you have the left translation, then you turn x into x minus, in this case, b. I'm sorry, plus b. Okay. All right. Now, that's it. Give me the animation of this curve. Give me the animation of this curve. What does it mean by animation? I don't want to get just a fixed translation. I want like animation. I want it to translate, move continuously. How can I make, okay, let's look at the right one. Okay, let me turn this one to a new page. So now I have a parabolic curve, y equal to x squared, right? But I want to make this an animation just like you do in, like, I don't know, some video editing tools and stuff. I want this thing to travel to the right. Very nicely. How can you turn this into a continuous animation traveling curve? I just want this parabolic curve to travel with time. So the idea is very simple. Let's say that at here, instead of having a fixed translation, you just turn this translation into a function of time. One more time. If I say, I just want to call this displacement or this translation to be some number, let me call s for now, some distance s. But then this distance s depends on time. So all you need to figure out is how fast you want the animation of this parabolic curve to be. So you can define the velocity of this. I want this to travel off the screen with this speed, v. And time just keep going, right? Time never stops. Once you know the velocity, you can calculate the displacement by take the velocity, multiply by what? Time. You guys with me? Okay, you guys. So if I know the speed of this thing, all I need to do is just multiply by time. So I know exactly what is happening at time t. So at time t, the displacement will happen already at the distance of s. So what is this blue, dark blue curve here? Is going to be y equal to x minus vt squared. You guys with me? And that's it, done. Done in the sense that from now on, whenever you see this here, x minus vt, you see an animation all the time. Voila. That's it. X minus vt. That is the function at the starting point of y equal to x squared, because you can set t equal to 0. That's your starting point. But time never stops. So it's going to travel. So that means is the x squared curve, parabolic curve, that is moving to the right with the speed v. Done. And I say, well, Ajahn, I don't want this to move to the right. I want it to move to the left. Can I do it? Of course. X plus vt, the whole thing squared. Okay. And this is always. All right. One point before we jump back to our handout. The problems, man, sort of the things that make these subjects suddenly difficult. Well, it's not super difficult, but it's just like sort of somehow it's more difficult than other because at this point you are dealing with two variable function. I don't know, have you done this anywhere else, but this is the place that you're going to have to deal with x and time. See? So y is function of two variable. Oops, sorry. That make it complicated automatically. Okay, all right. So let's jump back, and I hope by doing this, you start seeing what I'm seeing here. Now you should be able to answer this one right now. So as you say, well, Ajahn, at time 0, the pulse look like y equal to f of x. What should happen with this pulse at later time? You see it? Done. You just turn x into x minus vt. If this pulse is traveling to the right. And that's the conclusion that I can draw here. If you see function that looks like x minus vt, that is the right traveling wave. When they say right, mean positive x direction. And if you have the function that looks like x plus vt, that is a left traveling wave. That's a negative x direction movement. Whenever you have function that looks like two variable function of space and time like this, you can call this a wave function. Well, of course. All right. But every time you look at this wave in a static form, just like you see in the book, that is, here we go, come back here. Whenever you see this, what you do is you have to take a snapshot. It's like you're taking a picture of the wave. So that means this form of the function is just one moment in time. So you take a snapshot of it. So that means that's why every time you can draw a wave, that means you already freeze out the time variable. Okay, you guys with me? Every time that you can draw a wave, you have to stop the time because waves never stop. Waves always travel. That's the key. You cannot stop the wave. Okay, the only way that you can draw this wave on the screen, on a paper, you have to freeze the time. When I say freeze the time means you have to pick the time that you want to describe the wave. Otherwise, it will be an animation at all time. Wave is always an animation. I mean, it has to move. You cannot stop the wave. And every time you freeze the time or you pick the time that you want to draw the wave, you are generating a waveform. It's the form of the wave. Now you want to see, hey, what is the shape of the wave? Just take a picture of it. That is a function of x alone. You eliminate time variable out. You generate a waveform. Okay, sounds cool? All right, let's practice a very quick, simple exercise, but you should be able to answer with confidence now. If at time 0, you have a transverse pulse, whatever pulse it is, that look like this. This is a waveform at time 0, which is fine. If this pulse traveling in a positive x direction at the given speed of 4.5, what should be the function of these waves at any time? So you should be able to write the answer right away. Here we go, guys. It's simpler than you think. Done. Okay, you guys. Okay. If you guys okay, say 1. Just press 1. I want to sort of send 1 in the chat room or something. But that's it. You just turn x into x minus 4.5t. And you are generating a pulse traveling to the right, positive x direction with the speed 4.5. Yeah, maybe it looks too easy, but that's what it is. Try again. Here. Now, if you are given, like, you are thrown, like, at you with a function look like this, blah, 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 blah. They say, hey, determine the direction of the wave. You look at this one, Ajahn, it's x plus vt. when you have a positive sign, when they say positive means x and t are the same in sign, you can say this is going to be negative x direction. Okay, good. What is the speed of the pulse, guys? V is 5 meters per second. Done. You just read these numbers out. That's the speed. Okay. All right. Try again. Now, let's apply this to sinusoidal wave, shall we? Okay, almost done, guys. Here we go. Look at this. You have an orange one. This one starting from 0, 0. It looks good. All right. And I can say, Ajahn, this probably like if you have like the height of this one to be A, let me call A for now. So that means the bottom of this one will be at negative A. So I can say the sine wave that you're looking at, the orange one, will look like A sine somehow X. Okay. But then, Ajahn, I just want a freedom of stretching or compressing the sinusoidal wave. Okay, so what does it mean? It means I just want like a parameter or some sort of like a tunable numbers that I can adjust the size of the wave. So, okay, I can do that for you. What I can do is I can just give you some numbers in front of the X. And by having that numbers in front of the X, then you can adjust the K parameter. Then you can adjust the size of the sinusoidal wave as you like. Okay, you guys with me? Now, if you're okay with this, let me sort of give you an overview a little bit before we move on. Let's come back here just for fun. Okay, just to compare very easily, if you have sine X and sine 2X, what's the difference between these two? Ajahn, what you're having over here is if, okay, let me write the red one to be the sine. Okay, that's a sine. If the red one is a sine X, what should be the sine 2X? What do you think? Well, Ajahn, that's not too bad because when you have the factor of 2, whatever happens before at X is going to take half of that to accomplish the same value of the sine X originally that you have. So that means it takes shorter amount of X to accomplish the same effect as the function without the number 2 in the front. So you guys sort of get what I'm saying, right? Yeah, right. Because you have the factor of 2 in the front already. So the X take only half the amount that you used to have to accomplish or to get to the same value of the function before. Yes, so you get compression. So that means the curve of the sine 2X will get half the size of the original side of X. So whenever you have this, it's going to get, see, you can squeeze in the whole thing, squeeze it, you double it. So pretty much, so you double everything. So there you go. So you get the compression. So that's why I'm saying the parameter in the front will give you an adjustment of how you want to compress the sine function. Okay, sounds good. All right, so that's what it is. Now let's come back here. Now I give this one to you. Now is your job. Give me the animation of this sinusoidal wave. I want the blue. I want the blue. Well, Ajahn, let's do it. It's going to be A sine K X minus VT. Done. With me, guys? That is a traveling sinusoidal wave with the speed V. Cool. And that's what the simulation showed you before. All right. I hope it works. I don't know if it works or not, but I hope it works a bit. So let me show you by going back to this simulation one more time. I'm going to freeze it here. Okay. That is a sinusoidal wave. Looks nice. Okay, I'm gonna just move it in time a bit, one bit at a time, one bit at a time. And all you can see is just like you want to translate this curve to your right. That's it. So I'm just eh, 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 eh. So actually, the wave that you see is nothing more than just a traveling sinusoidal wave to the right. Very nicely. I hope you see this. Yeah. Uh, uh. Okay, sounds good. What is this one here? Oh, that's already. Oh, there is a step button there. Sorry, I didn't see that before. Okay, here we go. All right, so that's what I'm doing. I'm just going one step at a time. All right, and you can see each step that you look at this one is just the sine wave traveling to the right. That's it. Okay, so that's what you have. This one. Okay, so now I can just give you some terminology, and then now you can speak the language of waves very easily here. So first, if you measure the distance between two adjacent points that look alike, for example, if you want to measure the distance between peak to peak, okay, or you can do the bottom to the bottom, that distance we call wavelength. We use the lambda for that. That's the wavelength. Okay, and the A that I say, that's the height, the highest point that the element can travel up and down. You can call that amplitude, because that's the maximum value of the numbers that you can get in front of the sine and cosine function. The value of the sine and cosine functions is only between -1 and +1. So once we have the A in the front, so that means this function can give you the value between -A up to +A. So the A is representing the amplitude. It's the maximum displacement possible for the element in that wave. Okay, sounds good. Next. But then it's a two variable function. What you're looking over here, this is the X, right? In the dimension of the space. It's a distance, right? Traveling distance, on and on. You can look in terms of the time dimension. So now this is the one thing that you have to be careful with a bit. Look at the x-axis over here. This is now with time. But then people seem to get confused between this one and this one. This one is easy. The reason this one is easy because it's simply you just take a snapshot of the wave, right? And you just take a snapshot, bam, and then you're done. You get the waveform, looks nice. But the question is, how can you draw this curve when the horizontal axis is time? How do you get to this wave? And that's the question. Okay, so once again, I just want to bring you back to the simulation. Okay. Here. So you have to be able to looking at, because, okay, just follow me a bit here. To get a waveform, you take a snapshot. When you say you take a snapshot, mean you freeze the time. Okay, you pick the time, right? You freeze the time, you get the waveform. So you have to do the same thing with the time dimension. If you want to get what is going on in time, you have to freeze the X. You guys with me? Okay. When you want something to sort of express things in X, you freeze the time, get rid of the T variable. So if you want to look at something happen to T, you have to get rid of the X. So this means you have to somehow pick the X. When I say pick the X, mean you have to pick a spot on your wave. When I say pick a spot, you can see, pick one, pick the position. So just to make things a little bit easier, I'm just gonna pick the leftmost green dot. That's when I pick X equal to 0. Maybe that's my 0 position. So I'm just gonna, hey guys, looking at that green dot on the leftmost, just that dot. When I say only look at that dot, means I already say, hey everyone, look at the position of X equal to 0. See, that's what I mean by freeze the x. Don't look at other points. Don't look at other positions. I don't care. I only care what is going on with x equal to 0. And I let it go. Bam. You see what happened? Don't look at any other points. Just looking at that green dot. The displacement of that green dot up and down, that is a function of time. See? Okay, you guys with me, huh? So you have to freeze the x. Pick the numbers for the x. Once you pick the number, then it's like you staring at that x. That x still moving because it's a function of time. And then you plot the displacement over time. Then you get that curve that has a horizontal axis to be time. All right, you can pick any x you like. You can pick x equal to 0.5 meter, 1 meter. That means you staring at that spot. And that element on that string will still moving in time. Okay, guys? All right, if this is good, then now you know how can you generate this curve. This curve coming from staring at x equal to some number, and then that dot is still move up and down in time. And then you take that displacement, plot it against time. You get curve anyway, but it's still sinusoidal because you generate everything from sinusoidal wave. So once the horizontal axis is time, if you try to measure the same position on the curve that adjacent to each other, yeah, the two adjacent look alike on the curve, you get this, well, I don't want to call it distance anymore. You get an interval of time that complete one cycle, right? So this means the curve from this, from the red dot, just go down, go up, and come back down to the second red dot right there. That's complete one cycle. This one, we call it the period. Okay, the time that it takes to complete one cycle. Very nice. You can pick any 2 points, like between two black dots if you like. The A still be the amplitude because that's the maximum displacement in the vertical direction. That's inconsequence for now. However, you already sort of learned before from, well, some circular motion or simple harmonic motion and everything motion, that the period and the frequency are just inverse of each other. The period is time per cycle. The frequency is a cycle per time. So that means F and the period T is just inverse of each other. Okay. And that's it. With these two, I can actually express the speed of the wave or the velocity of waves using the parameter that I just introduced, the wavelength and the period or the frequency, by a very simple math. You guys, give me the speed of wave. Speed of wave, just think about it, okay? The wave can travel one wavelength, see, one wavelength. How long does it take for a wave to travel one full wavelength? Of course, then it's gonna take one full period because that's everything is one cycle. So that means you just use the simple math of the speed is just the distance over time. When the distance is one wavelength, one lambda, you're gonna take one period of time. So it's a lambda over period, give you the speed of wave. Or you can flip the period up to the frequency. So that's why you have probably have seen this one before, V equal to F lambda. That's the speed of wave. But it's nothing, it's like a not spatial formula on anything. It's just distance over time. Done. All right, cool, guys. Nice. Okay, if that is good, the last stop. All right, I'm going to pretty much get everything all together and give you even more vocab in physics, right? We get some names that you're gonna talk about. Okay, this slide might look a little bit confusing, okay, but don't worry about it because what I can discuss is this. Yeah, this one looks pretty bad. Yeah, I can see that. Okay, so let's come back to this a bit, okay, before going to any other point. I said at time 0, the sinusoidal wave look like A sine kx, right? Now I'm going to sort of crack this one out. What is actually the K in sort of like, physical parameter? Now you think about it, this is the numbers that just give you the sort of compression or stretch, whatever you like. But we already learned about the wavelength. The wavelength is the sort of like a distance, right? For one cycle. But then don't forget that the whole thing is behind the sinusoidal function. And we have already learned when you go full cycle, the angle that comes behind the sinusoidal will go from 0 to 2 pi. So every time you go around complete 2 pi angle, that is equivalent to one cycle. Everyone with me, yeah? So the 2 pi behind the sign represent one full cycle change in the angle. But in physics, we don't want to use the angle because the angle is pretty much geometry, sort of angle. So we want to call this a phase. But I mean, in your head, it's still angle anyway. So the phase is like when the phase of the sinusoidal function change from 0 to 2 pi, you complete one full cycle. But you already learned that, Ajahn, one full cycle, the wave must have traveled by the distance of one wavelength. So that means the x must be exactly 1 lambda when kx is perfectly at 2 pi. You guys with me? When x is 1 wavelength away, that will mean that the angle, the phase, the angular position, the phase of the wave must be already 2 pi away. So that's why I can say, here we go, k is just 2 pi over lambda. You guys with me? Let me just plug this one in. Oh, let's plug in this one here. Bam. That is why the k that is in front of the x can actually reveal the wavelength of that wave. Okay, very good. So far, so good. All right. Now, last stop. Once I know that the k is 2 pi over lambda, now focus on the animation that we have. Here we go. So that's my animation, right? So I'm going to pull that one down here and we're going to rewrite it again. It's a kx minus kvt. You guys with me? Right there. Okay. The k is 2 pi over lambda. That's done. Now let's see what is the kv mean. So I'm going to pull this one out, kv. Okay, k is 2 pi over lambda now. The velocity, we just learned that it is f lambda. You guys with me, yeah? So actually the lambda cancel. So I am left with the 2 pi f. Does it sound familiar to you? 2 pi f. That actually is omega. Is the angular frequency or angular speed, if you like. So in conclusion, I can actually re-express the animated sinusoidal wave that has the form that looks like this. Here we go. There's so many things right now. Yeah, kx minus omega t. All right, so let me sort of flash back here. So I can once again circle back up to the top here. So this one can look like a sine kx minus omega t. Here we go. I hope this complete the sinusoidal wave animation, all right, traveling wave, blah, blah, blah. So from now on, whenever you see the sinusoidal function that is representing a traveling wave, you can actually read out the information of the wave by looking at What is the number in front of x? What is the number in front of t? What is the a? And everything else about the waves is in here. Isn't that cool? Okay, come again. All right, let's go back to the slide and the handout. It looks messy a little bit here, but I hope it works now to your eyes. This is the same proof, but I think this, well, I'm not trying to prove anything. Try to say that every one wavelength, the key of this one, the whole thing is here. That's the purpose of this. It sounds sort of, this is bad. All right, so the whole point is this. The displacement or the distance of one wavelength equivalent to the 2 pi rotation of the angle behind the sinusoidal wave or sinusoidal function. So k lambda is 2 pi. So the k is 2 pi over lambda. We have the name for the k. We name the k the wave number. Okay, so I think this is the last term that I want to introduce to you. Wave number, that's the k. And the k is 2 pi over lambda. All right. Okay, very good. And that's it, guys. We know the omega, we know the k. We can write everything either in the x minus vt, which is now we agree, every time you see x minus vt, something is traveling, is animation. Or I can make it a little bit sort of like nicer, look like a kx minus omega t, that is fine too. Okay, you get everything out of this by k is 2 pi over lambda, omega is 2 pi f or 2 pi over t. In some textbook, they might want to rewrite the whole thing sort of out. They don't want to put it, leave it as a k. They don't want to leave it as the omega. They might want to express everything sort of explicitly if they want. So that is fine too. Okay. Now, the last point before everything's sort of like done here, you probably notice that there is an extra phi naught right here. Hey, there is a phi naught. What does this do? The answer is your starting point. What I'm doing over here is I rely on the sinusoidal function, right? But in reality, sine and cosine are exactly the same, just sort of displaced by a little bit. Or you can say, Ajahn, I don't even want to start with sine or cosine. I want to start with somewhere in between. So that phi naught will give you an adjustment of where do you want to start. Why is that? Because I can set x equal to 0, t equal to 0. So that means that is your position of x equal to 0 at time 0. Where is your value of the function? The function will go to a sine phi naught. You guys with me? So the phi naught will give you the initial phase or initial angle that the wave should be at the starting time and at the starting point. So that's why the phi naught can be an initial phase, or you can say like a phase constant or something that you want to add on top, that you want to do like a custom waves that you want to start your wave at some point. I hope you see this. All right. So I can make this a little bit clearer by once again, go back to this. So if I freeze it here, if this is my initial form of the wave that I want to start with, this is the sine, just like a regular sine wave. But some of you, I don't want to start here. I want to start like somewhere here. So that's when you have to adjust your phi naught. No, I don't want this. I want to go from the bottommost and start from there. That's fine. You just add some angle to it. All right. And of course, everyone knows if I add the whole thing by pi, that's half the cycle. You start from the side, but upside down. Okay. So that's when you choose the phi naught to be 180 degree or pi. Yeah. You see what I'm trying to get to. Oh, but I don't want to do that. I want to start from the top. And that looks like a cosine wave. Then you just add pi over 2 to it, or you can do 3 pi over 2 to it, on and on. So that phi naught will just sort of give you where do you want to get things started. Okay, so that's your fine tuning. However, in reality, if this whole thing just continuously move for the purpose of, well, wave description, that has no impact on the form of the wave. It's still representing the same wave anyway. Okay, cool. All right, very nice. I hope. พอรู้เรื่องไหมอ่ะ I think it's okay, right? Not too bad. All right, so that's in terms of introducing to you guys how to describe a wave using just sinusoidal function. And today you see an animated waves. Wave never stop. Okay, so to stop the wave, you have to either freeze the x or freeze. Well, freeze the x is not going to stop the wave either. You have to freeze the time, right, to have the shape of the wave captured. Okay. All right. Let's practice a bit. Okay. All right. And I hope you see it. I hope it's easy now. Okay. Let's answer this. The ocean waves with a crest to crest. Okay. Crest is just the peak of the wave. The crest to crest distance of 10 meters. So it's already give you the lambda over here. That's good. And can be described by the following sinusoidal function. When you look at this one, oh, John, that's not bad. It's in the x minus vt form. Okay, let me sort of write it side by side here, x minus vt. So it's even better that you know the speed of the wave right away, right here. Okay, but anyway, keep going. A, what is the wave number? K is 2 pi over lambda. So it's 2 pi over 10. That's it. Done. That's the wave number. What is the velocity of this wave? You can just read it out. The V is just 1.2 meter per second. Okay, I can write down the units as well, just to make things clear here. What is the angular frequency, guys? Now, there are so many ways that you can get to the angular frequency, because the omega is the numbers in front of time. So actually what I can do is I can sort of express this one out. Write it like this: sine 0.63 times x minus 0.63 times 1.2 t. You guys with me? Okay. And if you want to read this one out, the numbers in front of t, that is your omega. That's done right away. So omega is just 0.63 times 1.2. Cool. Or because omega is 2 pi f, if you want. Okay. But v equal to f lambda. So that means f is v over lambda. You know the v from the part B. You know the lambda from the problems that gives you. So you can say the omega is 2 pi v over lambda if you want. Okay. However, this one will sort of like go around the world, just, you know, to get back to the original, I mean, same answer. Because you can then plug in 2 pi v, which is 1.2. And the lambda that you got is just 2 pi. Oh, just 10. Okay, sorry, just 10. Oh, are they the same? That's a good question. I hope they are the same. That would be weird if they're not. So I hope the mathematics that's given from that function is correct one. Oh, I never tried this before. Yeah, I hope it works. Yeah, that looks good. Okay, they look okay. They're okay. They're the same. All right, but this examples is kind of like weird in the sense that instead of using the pi, they just try to hide it under like 0.63. Okay. So pi is about 6.14. So it seems to work. But either way, you get the same answer anyway. All right, part D and part E. All right, I probably not going to ask you to do this in the exam because you can plot it using mathematics sort of plotting tools that you can find it online and anything. But now you know what it means by the waveform. When you say, what is the waveform at t equal to 0, means you have to substitute t equal to 0 into your equation. At least you know that it looked like this. See, it's x0. So you reduced the two variable function down into a single variable function. So that means you get rid of the t variable. So at the end, it will look like 0.8 sine 0.63x. There, that's it. So the t, the time variable, will disappear from your equation. Same thing with the t equal to 2 in part E. You just substitute 2 in there, t just disappear. Okay, so you're down to a single variable, and that is your waveform. Cool. All right. Next, last stop. You guys, today is not too bad. Yeah, I hope it's kind of fun. It's like you're learning mathematics more like. Okay, what you have learned here, you take the information from the right side of the equation. See, look at this one. You can read this. You can say that's the amplitude. You can read this. You say that is the K. You can read this. That is the velocity. You know the omega. You know everything about the wave. You know how fast waves travel, the lambda, the period, the frequency, the amplitude, everything. But you haven't talked about the value of this whole thing on the left yet. And that is the last information that you can get out of this line. What is this? What is the y of xt? Well, Ajahn, is the vertical displacement, because right now we are focusing on the transverse wave. So whenever you plug in the x, you plug in the t, you're going to get a number, one number from this. That number give you the displacements. And because we are focusing on the transverse wave, so it's going to be a vertical displacement. That is the reason why we put y variable in there, just to clarify that, hey, this is the y direction, vertical direction. So that is it. The last portion of this one is, what you're talking about over here is, here, this is the y, right there. How tall of the elements that you're talking about at position x at time t. You can calculate that by plugging in x and t that you like. Okay, so last question that you can ask actually, but Ajahn, if I would like to calculate the velocity of this traveling string itself, what I'm talking about is, I want to know how this thing is moving, not the wave anymore, because the wave is already in the horizontal direction. It's just traveling to the right. But now I want to know how the elements of the spring is actually going up and down, up and down. What is its velocity? What is its displacement, and blah, blah, blah. You can start from this, because y is the displacements, right? So you can get the velocity by doing the derivative of the displacement or the position. That's it. So that's it. Just take one derivative. The only thing that's going to look a little bit different is you can see that the D operator over here looks a little bit curly. The reason for this is because this one, we call it the partial derivative. This is partial derivative. For those of you that maybe done calculus 2, maybe have to seen this, or calculus 3, but if not, that's okay. But the key is, the reason that we don't want to use the D sign anymore, because you are dealing with the two variable function. But for now, because the speed you can get it from derivative with respect to time. So in this case, you have to let the x sort of like out of the picture. You don't want to get x involved in this derivative. So that's why we call it the partial derivative, because it's going to take the derivative with respect to t, not the x. So you treat the x as a number. Okay, so this one, x is treated as a constant. Think of x as just number. Don't worry, just forget about it. It's not a variable anymore. So what you do is you take derivative of the y with respect to time. So just do derivative. A is just stay there. Derivative of sine, you get negative cosine. That's already there. Okay. And everything just follow. But don't forget, I'm sorry, there's no negative here yet. Sorry. And then you do the chain rule. The chain rule will give you the negative omega out. So that's why there is a negative and then omega in the front. That's coming from the chain rule. You guys with me? Okay. All right. So that's what it is. So you just take the derivative of the y with respect to time. Treat x as just a number. And you just differentiate it. And you get the transverse speed, the vertical speed that we are looking at. And of course, whatever numbers that go into the front of the sine and cosine will give you the maximum value all the time. So if you look at this number alone, that will be your maximum velocity possible. That's why I sort of put a note in here that omega L will give you the maximum transverse speed. Okay. And now you can go one step further because you already have displacement, you have velocity. You can do the acceleration as well, right? Because don't forget, the element move up and down, you must have some acceleration because it's a simple harmonic. So you differentiate that velocity one more time. And don't forget the chain rule, you get extra omega out. So by doing that, you get 2 of the omega, so it's omega squared. Derivative of cosine, you get back to the negative sine with the negative omega out. So this is the answer. I mean, the final expression for the acceleration look like this. Okay. All right. And then one cool thing about this one is you can actually link between the acceleration and the speed and the displacement simply by using, well, not acceleration, of course. This give you the relationship between the position and the speed directly without going through time. So that is a nice expression. Okay. But this one, the reason I put it here because it's just convenient that whenever you know your transverse position, you will know the speed automatically. So I'll give this formula in the exam paper so you don't have to memorize it if you don't want to. But think of it like a shortcut that going from the displacement directly to the velocity of the transverse velocity or transverse speed directly from the transverse displacement. I have to put the transverse all the time. Okay. But just to make things a little bit clearer to you guys, make sure that you don't mix between two velocity. There is the velocity of waves and transverse velocity. Okay, these are the two things. And I think this is the key of the whole waves business over here is there is the wave traveling velocity and there is a transverse with the subscript here speed. Okay, these are two speeds. But as I said, the whole thing now built into this equation right here. Just only one line of the equation can describe everything. Isn't that amazing? I mean, I know I like this one. Okay, the characteristic of the waves on the right hand side of this equation. Okay, and it gives you the position of the elements in the medium. Once you know the displacement function, you can find velocity and acceleration very easily. Okay, and I think that concludes pretty much everything about waves. It's just mathematics, all right? But I hope it's a good math, I think. And it seems to me this is the only place in maybe, well, high school physics, if you like think it that way, that deals with two variable functions. I don't think there is any other topics that do two variables function. So that's why this topic is automatically difficult back in the day. I don't know, anyone sort of give you like a quick note like, hey guys, we are about to deal with two variable functions, so things gonna get tough and rough from now on. But it's harder than usual. Okay, all right, so let's practice a bit, all right, and we take a break. But I hope you learned. I think this is everything about sinusoidal wave in the sense that you know how to describe it, or you know how to read the information out of it. So you should be able to do a lot of stuff here. Okay, so oh, like try this one, just like, yeah, throw information at you and just draw an expression of the wave function. So you have a string driven by the frequency of 5 hertz. So that's nice. Oh, okay, that's F. The amplitude is given. That's nice. That's A. And the speed of wave, oh, that's good. That's V. Determine the angular frequency, the wave number, and the expression of the wave function. All right, so this one is sort of like we're going backward a little bit. So let's try that. So the frequency is given. So omega is automatic because omega is 2 pi f. So it's 2 pi 5 hertz. So it's 10 pi radian per second. Done. What is the wave number? Wave number is K. K is 2 pi over lambda. Okay, okay. Now, you want to get lambda, V equal to F lambda. So the lambda is just V over F. The speed of the wave is given to be 20 meters per second. The frequency is given to be 5 hertz. So actually the lambda is 4 meter. Perfect. So just plug it in here. 4 meter. So it's pi over 2, 1 over meter. Let's do, well, let's do 1 over meter units. There you go. And that's it. Write an expression of the wave function. So I can say y of x and t, two variable functions, is just the amplitude A sine, you can pick cosine if you like, doesn't matter, kx minus omega t. Done. And you probably wondering, Ajahn, why you pick negative sign? Okay, I don't know. You can do positive too, because this problem doesn't specify which direction you want this wave to travel. So you can pick negative or positive, up to you. But the form of the wave look like this. Isn't that cool? I think it's kind of cool. All right, and one more stop before sort of like we going to the next exercise. Actually, for those of you that like and don't feel like this is already heavy in terms of numbers or formula, I can add one more to it. I'll give you one more formula of this one. For those of you, some of you seems to prefer the other sort of, there is an extra form of this V equal to F lambda that you can add on top. What I can do is I can multiply and divide this expression by 2 pi. Okay, so I multiply by 2 pi divided out by 2 pi. And then you can see that the 2 pi f is already omega. And 2 pi over lambda, that is your k down here. So actually, it's the same thing as omega over k, if you like. Okay, but it seems like from experience, you guys are more familiar with V equal to F lambda. That's why we stick with the V equal to F lambda most of the time. But once you sort of see many problems that dealing with omega and k, sometimes you might just want to take the ratio between omega and k and then get right to the speed of the wave. All right, cool. Try again one more. But I think at this point, you should be able to pretty much extract all the information about waves, sinusoidal waves, very easily. All right, so don't be afraid now. You have a transverse wave on a string described by the following wave function. Determine the transverse speed. Okay, now that is a keyword of transverse. Okay, and acceleration. Okay, so when you look at this one, you think of the y. So it's a v in the y direction and the a in the y direction. So in some textbook, they might use subscript t, but that's okay. All right, you can use y or the t just to emphasize that, hey, this is not the speed of the wave, it's the transverse speed. So it's the speed of the element of the medium that is oscillating harmonic up and down. Okay, so let's get to it. So this one is a nice thing is I'm going to sort of review how to do the derivative. Yeah. Okay. So the v sub y is just dy by dt. See, I'm doing the curly d because this derivative will be taken with respect to time, not the x. You can treat x just like a constant. So take the derivative of this. 0.12 just stays there. I'm just going to omit the unit. Okay. Derivative of sine, you get cosine. And you get everything else in here. Okay. And I'm going to follow by the chain rule. Chain rule is I'm going to take the derivative of the function back in there by dt. See, that's the chain rule. Okay. And for those of you that sort of learn this in Thai, just this is dip side, yeah, dip side. Yeah. So you have to dip side too. Yeah. But when you do the dip side thing is you take the chain rule just with respect to time, not the x. And of course, this term alone give you 4 pi. X gone. So the answer is 0.12 4 pi cosine pi over 8x plus 4 pi t. Done. Cool. And if you want acceleration, you do it one more time. You take the derivative of the velocity with respect to time. So we're going to follow one more derivatives into this one. So 0.12 is still there. 4 pi, no change. Derivative of cosine, you get negative sine. Here we go. And I'm going to follow by, once again, the chain rule, which will give me another 4 pi again. You guys with me? Dip side. Yeah, I'm going to do the chain rule. I have to take the derivative of whatever inside the sinusoidal function there. So that means I get extra 4 pi out. So in conclusion, I have 0.12 4 pi square sine pi over 8x plus 4 pi t. And from this point, you can substitute time and space whenever, wherever you like. But this number is bad. At 0.2 second, 1.6 meter, you just plug into that expression and then just punch the calculator. Yeah, that's what has to be done. All right, but I hope this is clear what it means by transverse. Yeah, transverse speed, transverse acceleration, you get from derivatives of y, which is the transverse displacement. And now part B, what are the wavelength, the period, the speed of the, oh man, what this thing, you can just read it out. Let's go for it. Let's do practice one more time. The numbers in front of X is K right here. That's K. Number in front of T, that's omega. Okay, cool. Okay, so I can say K, which is 2 pi over lambda, is just pi over 8. There you go. Yeah, the numbers in front of X. Oh, okay. There is a question comes in, will there be every formula in the formula sheet? Yes, there will be. Yes, you don't have to memorize it. Or you don't even have to differentiate yourself. I will list them all here. The Y, the V sub Y, the A sub Y will be in there. Yes, yes. Okay. All right. For those of you that feel uncomfortable doing the, derivatives or chain rule, it's still there. I mean, the formula will be in there. Okay, the K is 2 pi over lambda is just the number in front of X, which is pi over 8. So that's it. So we just, the lambda will be 16. Yes, done. Now, you want the period. You know the omega is 2 pi over period. And that is just 4 pi. That's a number in front of T. So you over here, the T is just 1/2 second. Nice. And what is the speed of the propagation? Now I can do shortcut if you like, is omega over K right away. Or you can do lambda over period, or you can flip-flop into frequency if you like, up to you. Everything is already known. So the omega is 4 pi. The K is just pi over 8. So the answer is 32 meter per second, of course. There you go. I can just add on top, the frequency of this one is 2 hertz, if you like. Yeah, just write out everything. Very good. Okay, so you can do V equal to F lambda. And it's just a 16 multiplied by 2. You get 32 anyway. Okay, you can do omega over K directly, or you can do F lambda if you want. See, I hope by having this sort of like concluded here at the end is just like straightforward. Yeah, I would say. Now you know how to read the information out from wave function. And I hope you see the connection between this and simple harmonic motion before, because they are pretty much, you can use the simple harmonic movement to generate the sinusoidal wave. And that's why sinusoidal function connecting these two kinds of, one is a motion, the other one is a wave. So these two things are closely related. Very nice. Okay, cool. Let's do one more. And we're going to call it done for describing a wave. Okay, and we'll take a break. Sounds good? I hope this is not too heavy for this morning. I hope you guys are okay. Sorry about the technical error for that simulation that's sort of wasted 5 minutes, 10 minutes. A transverse sinusoidal wave on a string has a period of 25 milliseconds. Okay, that's good. That's given. And the travel in the negative X direction. Okay, just read this one out and then I'll describe what this is about. With the speed 30 meters per second, that's good. This is V already. At time 0, a particle on a string at X equal to 0 has a transverse position. So actually this one gives you the Y. Okay, at 0, 0, you guys with me? Yeah, because that's at X equal to 0, at time equal to 0, that is Y at 0, 0 equal to 2 centimeter. And is traveling downward with the speed given. So actually this one gives you V at 0, 0 to be negative 2 meter per second. You guys with me? Yeah, let me write it out over here. 0.2 meter. This is the kind of information given. And now you sort of like, oh, okay, I understand what it means now. Okay, so first they say, hey, can you figure out the amplitude? And this is where the nice formula that I just sort of put the stars there comes into like a very good help here. You get the Y, you get the V. there is a relationship between the position and speed right here. This is a nice sort of like a shortcut, it's like a relationship between the position, the transverse position, and the transverse speed. So actually I can use this one right away. Very nice. So this is the good example to try that. So you say the speed is just omega square root a square minus y square. Okay. And from here, the speed is given to be -2. Okay, let's me omit the units for now. The omega is just 2 pi over period because it's already given. That's nice. Square root a square minus y, which is 0.02. See, this is how you can figure out the amplitude using this expression right here. All right. So I hope you see how to apply that formula right here. All right. Now for the part B though, they want to figure out that phi naught equal to what? Okay, for this one, I'm not gonna sort of showing you now because I think it will get more complicated out of nothing pretty much. But if you really like, I'll show you roughly what it means, but you don't have to worry too much about it because I think in the exam, we are not trying to do anything about the phi naught because like the key point of this one to take is the characteristic of the wave. Yeah, not like, playing trick with like, hey, when do you want to start the wave or something like that. But I mean, anyway, you can actually do it very easily now if you want, because you already know what is going on with y at 0, 0. So that means here, let me write it out like this. Y at 0, 0 is going to look like A, the amplitude, sine. Okay, let me write it in full first. It's a kx plus omega t plus phi naught. You guys with me? Okay. The reason for plus omega t because it's the negative x direction traveling wave. So that's why I take the positive sign to come between x and t. Okay, and because it's a 0, 0, so actually this 2 is gone pretty much. Okay, so you can substitute the number in there. The transverse position is 0.2 centimeter, so it's 0.02 meter. Amplitude is the whatever you got from part A. I hope it's here after doing the calculation. And that's when you can figure out the psi naught here. Okay, the initial phase angle. You can figure it out this way. Okay, all right. But anyway, don't worry about this one. I think this one, well, you can just park it here, just so you know, just sort of FYI, you can figure it out. Okay, now part C is more interesting. What is the maximum transverse speed of the string? Okay, but more interesting in the sense that you know how to read this one out, because we just said whatever the factor that come in the front of this expression, it will give you the maximum value no matter what. So the maximum transverse speed is just omega times the amplitude. So that's it. Well, okay, then the maximum speed is just omega A. Omega is known. The A is supposed to be known from part A. So you're done. Okay, so this is a bad sort of solving the problems, but I hope you work out the number later. All right, part D, the final part. Write the wave function. Not a problem, because the wave function look like A sine kx minus or plus in this case omega t plus phi naught. See, so this is a whole purpose of this exercise right here is just try to figure out all of the parameters that will shows up in the wave function. Once you know them all, you can write the expression of the wave function right away. See, the A is known, omega is known, phi naught is known, the K, do you know the K? Well, no problem, because the K can be found from V equal to omega over K. So the K is just omega over V. Omega is known, the speed of the wave is known, you know the K. So this is how you write the expression for the wave function.